Okay, thanks, Alex. Great to be here. And I prepared a talk, but please feel free to interrupt and make it a discussion. I have many things I want to say, but I'll try to give an overview of our thoughts on actual experiments on the cuprate superconductors. And this is work with many people, and hopefully I'll get towards the end to the latest PCS paper that I'm very excited about with Pietro and Maine. Okay. These are some of the people I'm working with. Maine Christos is a graduate student at Harvard. Zhuxi, you all know, one of the organizers, now joining Georgia Tech. Matthias Scheurer is now a professor in Stuttgart. Yeah, he gave the talk this morning. Pietro Bonetti is a new postdoc at Harvard. And Henry Shackleton just graduating tomorrow and will be at MIT next. Okay, so this is the famous cuprate phase diagram drawn by these illustrious authors of some time back, encapsulating many of the mysteries that we're still trying to understand. So on the overdope side, you have a Fermi liquid, which seems to be reasonably conventional. In particular, if you look at the Fermi surface, it obeys the Luttinger theorem. So if you just assume the electrons are free, you'll get the right Fermi surface. And one of the biggest mysteries really is what's happening on the underdope side, where at high temperatures you have this mysterious Fermi arc spectrum. So this means that there's been some gapping in what's called the antinodal regions, where there's no more Fermi surface. And this T star is determined by various methods, including the development of this spectrum, but also in the spin susceptibility, the optical conductivity, and so on. You see various gaps developing, hence the word pseudogap. Pseudo because, well, obviously there's some gapless excitations on these famous Fermi arcs. So the question really behind everything I'm going to talk about is, what is this state of matter that we're talking about here? Now, one point of view is, well, it's just some fluctuating mess of some autoparameters, stripes or superconductivity and so on. And okay, maybe that's the right way to think about it. But the point of view I'm going to present is that it's really a quantum state, which at low temperatures is unstable to the states that we see here. But of course, that's not such a new thing. Even the Fermi liquid, we know, is ultimately unstable. So, and we're perfectly happy to think of the Fermi liquid as a good quantum state. And I'm going to argue that's really how we should think about the pseudogap. So it's a quantum state in its own right, rather than the fluctuating of something else. But it's still at finite temperature, so that makes the statement not as sharp. But the question now, of course, is, with this approach, can you really understand something, at least qualitatively, about the experiments? Okay, so what are the models that have been around? There have been many, many models, and essentially all of them assume these arcs, the front sides of some hole pockets. So this is a unusual state of matter, postulated or obtained in various DMFT-like calculations, where you get spectra somewhat like this. And this introduces what I'll call backside problem 1, which I won't really solve, which is, well, what about the backside? Has the backside ever been seen in any experiment, the backside of this pocket? So the answer is definitely no in photo emission. And the question is, well, okay, is it going to be eventually seen? So I'm not going to solve that problem, but I'm going to assume that this type of pocket is a good starting point anyway to understand the pseudogap metal. So once you have such a state of these Fermi surfaces, these do not obey the Luttinger volume. That is, Luttinger would say you have holes of density 1 plus p, whereas the total density in these pockets is p, quite accurately from various measurements. Okay, so how do you account for that? So in some of these papers, there's things called zeros of Green's functions that appear in various DMFT type calculations. And those zeros allow you to fix the usual proof of the Luttinger relation. And so somehow the zeros of Green's functions are then playing some role in understanding why you have a violation of the Luttinger theorem. Well, so that may well be correct, but I view those zeros as some artifact of the approximation that you're making, and they're not really fundamental to the theory. What's fundamental to the theory is that there are a whole other sector of excitations that must be present. And the presence of these other excitations is made clear by a more general version of the Luttinger theorem, which maybe you can call it the Oshikawa-Luttinger theorem, which is a more general non-perturbative topological argument. And that tells you that every time you have a Fermi surface of electron-like quasi-particles, there must be some kind of spin-liquid state. In this case, since the deficit is exactly 1 electron per site in the Luttinger count, so that must be a spin-liquid exactly at half filling. Yes?
If they don't see the backside, how do they measure the area?
Well, they do see the end of it over here. And certainly so they just draw a straight line between the ends. Yes. Yeah. I mean, that's done in photo emission, STM. And if you just draw a straight line, you do get P.
Okay.
Yeah.
If you draw symmetrically, like
no, then you won't get the right answer.
yeah,
Right. Well. You won't get P. Right. Okay. I mean, there are also DMFT calculations. Well, no, they don't really have the DMFT. At least the eDMFT doesn't really have a very sharp resolution to really say what's going on. There's certainly a lot of low energy spectral weight here. Okay. All right. So this state of matter with spectator spin liquid is what I call FL star. And it's the state that I'm going to use as the starting point for everything I want to discuss today. And you can decide whether it's a good starting point for understanding many of the mysteries of the phase diagram. Okay, so one evidence for the presence of a backside is this angle-dependent magnetoresistance measurements. So unlike photo emission, ADMR doesn't depend upon electronic spectral weight. If there's a quasi-particle, it's going to show up. And at least these measurements, I won't go into any of the details, are best fit by some type of pocket model in the underdoped regime. In the overdoped regime, sorry, that's the underdoped this side. In the overdoped regime, the large Fermi surface explains everything much better, but very well, I should say. All right, so assuming we have an FL star state here, then at low temperatures, the question now becomes, how do you see what you see? One is high temperature superconductivity, the other, depending on the material, some kind of charge density wave order. And so you get some state here. Now you can also reach this point by starting from the Fermi liquid. We also know how to use BCS theory or Stoner theory to get from the Fermi liquid a D-wave superconductor. In fact, that was predicted for the Hubbard model, and also various types of charge orders. So now the starting point of all my discussion today will be the assumption that the state you get from this route and the state you get from this route are the same state that can be smoothly connected without any obvious phase transition. So, that need not have been the case. Certainly I had the hope many years ago, well, that maybe there will be some actual topological phase transition. This is a different superconductor from there, but there's essentially been zero evidence for that. So now we're going to assume that these two states really have to be the same state. And this turns out to put strong constraints, as we'll see, on the nature of this FL star state and the nature of this onset of superconductivity. So what we'll then find, for example, that the onset of superconductivity on this side is very BCS-like, whereas the onset here is not. But the BCS state itself is perfectly fine, both at low and high doping.
Question?
Yes?
So, Subir, are you saying FL star and FL are different, but once they superconduct, they become indistinguishable?
Yes, so if FL star and FL were stable down to 0 temperature, there would be a phase transition between them.
But once you make them superconduct, they just forget about...
It depends. I mean, you could get more exotic superconductors, but we're going to now look at the cases where you don't. Okay, so there is no phase transition here, but if you could get rid of superconductivity somehow, then in principle there could be distinct phases. In fact, the FL star that I'm going to use, the spin liquid I'm going to put, which we have learned from all the DQCP talks earlier in this workshop, are unstable. So in fact, the particular FL star state I'm going to use is always unstable at low temperature. Now, if it was a Z2 spin liquid, then it would be stable. And I've written many papers on Z2 spin liquids, and now you can ignore all of them, at least for the case of the cuprates. But the good old DQCP will actually, as you see, has many nice properties that completely fit this scenario that I'm presenting. All right, so but that connects directly to your question. What about the strange metal? Well, the strange metal we do believe is a transition between these two metals at finite temperature. This is quite similar to what Yahui was saying earlier today. But in Yahui case, it was FL and FL. There were two different FLs. This is, in fact, a little simpler. Here you have an FL star, and there's an actual violation of Lattice theorem, and here there isn't. And so this is the type of theory that, in the presence of disorder, gives you strange metal behavior, and that was the topic of my talk in the conference. And Avishkar also, and how you talked about it. So I'm not going to talk about this at all, but I'm going to talk about going down from here to here. All right, so in the end, what this is, if I go back here, this transition then is what I'll call a confinement transition. It's a confinement transition because there are some fractionalized excitations that have to be in the background because of the violation of the Lattice rule. And those fractionalized excitations must confine to give you a conventional BCS state. And so we want to understand such confinement transitions. So I'll begin by talking about actually something that's very well understood, and also the confining phase means thoroughly tested in experiment, and that's on the Kondo lattice. So let's just quickly recall, and I think there were also earlier talks like Tessa Cookmeyer in the workshop on this. So I'll quickly recall this. If you take the Kondo lattice, where you have a band of conduction electrons and a separate set of spins, which have some exchange constants with themselves, and then there's a Kondo coupling between the conduction electrons and the spins. So now let's take the limit of very small jk, which is actually the simpler limit, and imagine that the JH is such that these spins form a spin liquid. So then it's not so difficult to show that perturbatively jk doesn't do much. And so you just get this very simple decoupled state where the conduction electrons form a Fermi surface, and the density of the electrons C I'll call P here, whereas the spins form a spin liquid. This is some resonating valence bonds here, and jk is very small, and it's stable to small jk. So this is then, the almost trivial way of describing what you call FL star. I mean, the only content in it is that it's stable for small jk. And then at small jk, when these are coupled, you're violating the Lattice theorem. And you certainly do have a spin liquid that allows you to do that. And if you want to write down a wave function for this state, you just write down a wave function for free fermion wave function for C with volume P, and some good solar projected wave function for the Fs. All right. Yes?
It's stable, does this stability depend on the nature of this spin liquid?
Certainly if its gap is stable, but I haven't looked at all possible cases, but you get most, I mean, if you have a direct fermion spin-on, it's still stable too. Yeah. Yeah, okay. However, the state that's invariably seen in almost all heavy fermion materials is not that state. It's the confining state. And this is the modern language for it. The spin liquid has been confined, and the way it's been confined is by the condensation of a Higgs boson that completely breaks the symmetry in this, whatever the gauge symmetry is of your Z2 spin liquid. Most common case is U1, of course. And so this Higgs boson is a hybridization, roughly stated, of the, where is it written down? Yeah, here. So the Higgs boson is a hybridization of the F and C. Maybe you can call it a hybridization boson, and in past days it used to be called the slave boson. Anyway, so when this condenses, then you get a large Fermi surface. And in this case, the way you write on a wave function for this state is you take a Slater determinant of the two bands, the B will mix them, and so with that hybridization, you get a single Slater determinant, and you just project onto this F to one particle per site on the F. And there's been a lot of studies of this, and it's that projection that gives you the heavy mass, and you obey the conventional Fermi liquid, which is confined from FL star. Now, recently, there's been this very nice study that Tessa Cookmeyer talked about of cerium, cobalt, indium 5, where there is some evidence as a function of doping to going from a small to large Fermi surface in quantum oscillations and photo emission, I think, also. Anyway, but I don't want to go into that. All right, so the question now is, so I've given you an example of an FL star to FL transition, which is perhaps similar to this transition here, but this is for a Kondo lattice. So really the big question is, how do you do this for a single band model? And that turns out, paradoxically, to be a little more difficult, quite a bit more difficult. And there's various ways of doing it. The hand waving ways, you have a spin liquid, some spin-ons, you dope it and you get some holons, and then the holons bind to the spin-ons to form an electron, and there's density P of those bound states and they form a Fermi surface, and the spin-ons are still around. All right, so that's the picture, which has been around for a long time, but good luck with actually trying to compute with it, because you have to first fractionize the electron and then undo the fractionization of some of them, and so on. So there have been various methods that people have applied. I'm guilty of that also. But I think the method that really gives this answer to you already at the mean field level. And really, we want it at the mean field level because we're going to have to go beyond mean field to do the confinement transition to true confinement, where the spin liquid completely disappears. And that method is the Ancilla method due to Yahui. Okay, so what is the idea of the method? It's really extremely simple, and I'll try to explain it without any slave bosons. Where's Yahui? Something Yahui should have done this morning too, but okay, he's not here. Okay, so what you do, you take this, here's your Hubbard model, single band Hubbard model with, I'll talk in terms of holes of density 1 plus P. And then I just add to it a trivial insulator, meaning that you just get a bunch of round singlets. These are Ancilla degrees of freedom. The idea being is that once you have the Ancilla, just like also the case in quantum computing, the purpose of the Ancillas is to create more entangled states of the physical degrees of freedom. So the Ancilla will help us write down phases and gauge theories of the physical electrons in a much more elegant way than the hand-waving method I just described. All right, so you take some Ancillas with coupling J-perp. And so now, of course, when J-perp is large, they all sit in the trivial ground state, and you haven't done anything. So there are some extra states now in this new model, H Everett plus trivial insulator. the triplet states, but there's some energy J perp. And so we're going to assume that those high energy states are not going to play any role in any of the low energy physics I'm going to describe. Okay. All right, so now I'm going to do a canonical transformation. It's like the inverse Schrieffer-Wolff transformation. You want to pick this canonical transformation so that you have some new Hamiltonian of the 3 layers. And this has the advantage that the top layer is essentially free electrons. Okay, so now you're going to so you've gotten rid of the Hubbard U on the top layer, but the price you pay is you now introduce this Kondo coupling between the top layer and the first layer of spins.
How is the top layer coupled to Ancilla?
By this Kondo coupling, it's only coupled by this canonical transformation.
Okay, only.
Yeah, you can undo the canonical transformation and get back this model. So the physics we're describing, we hope, is just the physicals of this model. So you do the canonical transformation, that couples them. All right, and so then you get this simple Hamiltonian. There are many other terms, but you get free electrons on the top layer, and then they're coupled by JK to this it's not a ladder, it's a 2-dimensional bilayer antiferromagnet. And you can just do your Schrieffer-Wolff transformation. It's easier to go from bottom to top. You do the Schrieffer-Wolff transformation, illuminate these spins in a 1/J perturbation theory, and you'll find a Hubbard model for the top layer with U of order JK squared over J perp. Okay, that's in the appendices of some of our papers. It's really an easy calculation. So at least in first order in J perp, for a very large J perp, this is an exact mapping. You can go to any higher order you want, and of course you'll develop more and more complicated couplings. Needless to say, we haven't done that, but anyway, the general idea hopefully is clear. All right, so now of course, if J perp is really large, then it's not going to give me anything new. So now I'm going to assume that, if I had just a single spin coupled to these conduction electrons, we know what happens to JK. The Kondo coupling flows off to infinity when it's antiferromagnetic. So under some RG, we can imagine that even though we started out with JK much smaller than J perp, maybe it becomes larger. So you can just imagine what is the phase diagram of this more general model when JK is a bit larger? Because under RG, we do expect it to become larger. So now I'm going to draw the same phase diagram, but notice JK is now increasing to the left. When I had the Kondo lattice, I still had FL star to FL, but JK was increasing to the right. And so now I'm going to take JK increasing to the left, and now at small JK, I have, it's trivial. The spins, the extra spins just form a trivial insulator, and I have a large Fermi surface. But what happens at large JK? Well, at large JK, then the top 2 layers form a heavy Fermi liquid, because that's what spins do when they're coupled to a Fermi surface. They form a large Fermi surface. So the top 2 layers are, quote unquote, going to confine. And that's going to happen by the condensation of some Higgs field phi, which is just the hybridization of these 2 electrons. Okay, and now the magic is that what is the total density of electrons in this heavy Fermi liquid? Well, there's 1 plus p on the top, and there's p1 on this, so that's 2 plus p. You only measure modulo 2, so you have a small Fermi surface of size p.
So weird.
Yes?
So in the model, you're really just coupling the 2, so you have 3 layers.
Yeah.
But the bottom 2 layers are not equivalent. It's only
Yeah.
one leg which is coupled to.
Right. That's right. Yeah, they're not. That's how you have to. That's how I chose the model. That's how I did the canonical transformation. Here, the coupling was only with the top layer. That's my choice. I can choose the way to do it. That is the way we want to do it. And if you also, another thing I briefly mentioned, if you try to figure out what is the induced coupling with the top layer and the bottom layer, if this is antiferromagnetic, this is antiferromagnetic, that's ferromagnetic. So even if it is initially large, it will go to 0. So we just ignore it. All right, so now, so you should really view this Ancilla as a foolproof way of getting all the anomalies right. It's just because you've now violated the Lattice theorem, but it tells you, wait a minute, there's a spin liquid here. So you needed that. It's required by the Ishikawa-Lattice theorem, and there it is. So it's the bottom layer must form a spin liquid, and then you can get a small Fermi surface. Okay, so that's the world's simplest way to get an FL star in a one-band model, at least the simplest way I've seen. And now we can also write down a wave function for it. You take a stated determinant of the top 2 layers with this small Fermi surface size. Then you take your favorite spin liquid wave function, some free fermion pi flux phase if you wish. And then finally you project out the rungs into the singlets. So that's the action of all the gauge fields that I didn't mention. You can do this formally with lots of gauge fields, and it's even more complicated than what he talked about this morning. You get an SU2 cross SU2 cross U1 gauge field, but I won't show you any of that. But this is the wave function that you can work with. And now this wave function is a wave function only of the physical electrons. It doesn't involve, after the projection, the Ancilla spins at all. So it's a very simple wave function, at least to write down, which gives you a rather more entangled wave function for the physical electrons. All right. So once we had this wave function, I talked to Yasir. But this wave function is not so easy to work with. This projection is not as simple as the Gutzwiller projection. But Yasir and others have worked very hard on evaluating a few things with this wave function. I'll show you in a minute. So in particular, the kind of thing I thought you could now try to measure, these local correlations that appear in cold atom experiments. So this is the Hubbard model, where they see a pseudogap, what they call a polaronic metal. And in this regime, you get, this is a hole near the hole. You look at spin 3-point correlation function of 2 spins in a hole. And the colors represent the spin correlation function around the hole. And when you're at low doping, this polaronic regime, you have these ferromagnetic correlations. Whereas when you go to the Fermi liquid, it becomes all anti-ferromagnetic, if I remember right. Anyway, so there's some rather non-trivial evolution of these 3-point correlations at rather high temperatures in these cold atom experiments. And so there's this work by Yasir and Tobias and Ronnie, who computed this with this wave function. I know this a little bit better. This is Henry and Shiwei at Flatiron. Related methods, they've also done it. And basically, there's only one variational parameter in this wave function, which is this hybridization phi. And you can optimize that to get the best energy. And these are various correlation functions of the first and second neighbors that track the experiments pretty well. The other things we have done is also, this is an actual computation from an Ancilla model of the Fermi surface and its spectral intensity. We've also looked at the effect of the spin liquid on how it broadens these lines. We haven't studied really whether it reduces the intensity of the back. That's, I think, another thing that's very plausible, as I'll argue later. And then we've also looked at the spectral functions here in the antinodal regime as a function of energy and momentum. This is the famous data of Ziek-Shen, and all of these trends are very nice. And this is the antinodal region, this is the nodal region, the dispersion as a function of momentum, and really capture all of that quite well. In this same model that was used to fit exactly, you fit this Fermi surface, so there's some parameters for that, and there's a pseudogap that you fit, and that's it. And then the whole structure just comes right out. Okay, so that's just the FL star. And okay, you may not, I would say the main outstanding problem is to understand, what about those backsides? It's just a question of intensity. Maybe better experiments will see them, or is it something more fundamental that the backsides at these finite temperatures are very hard to observe in photo emission anyway. All right, but I'm going to talk about the backsides a bit more soon. All right, so now we want to go lower the temperature and start from this FL star state and go down to what's happening down here. So we develop a general framework on how to do this. Again, the framework could have been developed without ever introducing Ancillas, but Ancillas really made it very clear on what you need to do. Yes?
For the Ancilla wave function and the projected wave function, if it already is clear that this wave function can be exhausted of any local constraints?
No, I have no idea. What I can say is, I view the projection as a gauge fluctuation, and the reason why is the projection mild is what I can say. It's the same reason why the Gutzula projection for the heavy Fermi liquid is mild, because the gauge symmetry is Higgsed. So in this case, there's an SU2 gauge symmetry. Due to this between the top two layers, and that's Higgsed by this field phi. So there's an SU2 gauge symmetry between the bottom two layers, which is also Higgsed by the field phi, and the projection is like integrating about the SU2 gauge field on this layer, and since it's Higgs, we don't expect anything singular to happen. That's all I can say. Yeah.
So this projection is in the basis after you do the canonical transformation.
Everything is, yes. This is a slightly different approach, yeah.
So in terms of the original...
Canonical transformation, just view that as a, we've done the canonical transformation. Now we have a new Hamiltonian with lots of gauge fields, and we're solving this theory, yeah. And this projection, this is just a variational ansatz, which is motivated by the gauge theory. And it is precisely this wave function that was used in these numerical studies, which match quite well with both papers hopefully appear in a month or so. Okay. All right, so now we're going down. Right, so now at this point, we do have to make a choice for everything I've said so far. You could put your favorite spin liquid down here, it'll all go through. Now we're going to make a choice, and you'll see why. And the obvious choice seems to be that you should see the only spin liquids that's ever been seen on the square lattice in all the studies that have been done, and that's the Nail VBS DQCP. And so we're going to choose that, and we'll see that it has certain properties that are really fit the bill as far as the experiments are concerned. And we're going to use, so we've learned about these dualities. There's the CP1 way of doing it. There's the O5 nonlinear sigma model with Bezzamino term. But the simplest way is the original way of Affleck and Marston. Just take spin-ons moving in pi flux and coupled to an SU2 gauge field. So that's down here. That's the SU2n, meaning Nambu, as you'll see in a minute, it's acting on the bottom layer. And all the other gauge fields have been, as you're coming down in temperature anyway, have been Higgsed by phi. So we ignore those. All right, so now we know that this spin liquid is unstable to Nail or VBS. And now we're going to look to confinement to either Nail or VBS at low temperatures or low energies. And now we're going to see, well, what happens when you put charged excitations? What happens when you dope the system by the top two layers? How are they going to, can they confine this spin liquid? Well, how are they going to confine it? Well, again, it's the same old trick. You have to condense another Higgs boson that couples the bottom layer to the top two layers. And this Higgs boson will transform as a fundamental of the SU2 gauge field down here. And it's basically this one here. And this is the same, originally introduced by Wen and Lee in their theory of the pseudogap. They went ahead and then talked about a staggered flux spin liquid, which I will not do, because that doesn't fit the bill in many requirements. And also now it's known, as we heard from many talks, to be just unstable to a trivial monopole. So you really keep the full SU2 gauge theory in the pi flux and then condense this Higgs boson in the presence of the Fermi surface of the top two layers. All right, so now we want to write down a theory for these spin-ons and this Higgs field, and then use gauge invariance to couple them all together. And then you can also put in the hole pockets. And we did all of that in some paper. Yeah, this paper here. I'll just present some of the highlights. So first of all, let's just take the spin-ons. They form this pi flux phase, and this is the way you write it out in a manifestly SU2 gauge invariant manner. So UI is the SU2 gauge field. And this EIJ are plus or minus 1, chosen to have pi flux. Then what about the boson? And here's the most important point. The boson must also move in pi flux, because the composite of the boson and the spin-on is just the electron, and that must be trivial. So basically, the hopping of the boson becomes very similar to the hopping of the fermion. And then you can work out all the other projective transformations and get even the higher order terms. So the higher order terms, quartic terms, look something like this. And using all the projective transformations, you can write down various SU2 gauge invariant objects. And they give you, the side charge density, the bond current, and the pairing. And then you go ahead and minimize this with various parameters. And this is the kind of phase diagram you get. So when the Higgs boson is not condensed, then you have just the pi flux phase, which is either Néel or VVS. And when the Higgs boson is condensed, this is the simplest condensation, you get one of three phases. Why are there four? Yeah, okay. Yeah, there's two. So you get, first of all, you get a superconductor, and it's a D wave superconductor. It's not S wave, just D wave comes right out. This is, of course, known from the very early days of high TC, of the intimate connection with the pi flux phase and the D wave superconductor. And then you also get, depending on these quartic coefficients here, some staggered current phase that's never been seen. And finally, the third phase that you get, and this is the new result, is a stripe phase. You get a stripe order with pi 0 or 0 pi in the simplest situation. And you can put in, before I jump to that, and if you take the zero doping limit of that, this theory, this is what Zhu I think she talked about it. Then you have to turn down the Hubbard U, and then you can get a phase transition here between Néel or VVS and one of these states. And this is an SU2 gauge theory with NF equals 2 fermions and NF equals 2 bosons, and this could well be an actual stable DPCP. Anyway. What I was saying, if you take a more complicated case with a more complicated dispersion of the boson, you can even get various stripe phases. There's a lot of richness, of course. There's a lot of parameters. But you can get stripe phases with no other broken symmetry, which you don't get with any other spin liquid. All right, so that's the framework. And now let me address two very significant experimental issues. And then you'll see why, hopefully, in this part 4 and 5, why the existence of these spin-ons in the spin liquid is actually a very important requirement, that you can't understand what's going on without the spin-ons being there. So first, let's look at the instability to just a D-wave superconductor. So first let me recall, how do you get a D-wave superconductor from a Fermi liquid? Well, there's the large Fermi surface. The pairing gap goes to 0 along these lines, along the diagonals, and then you get these 4 Dirac points with highly anisotropic velocities, with this velocity being much larger than this velocity along tangent to the Fermi surface. Okay, so let's do that with FL star. So we just do the most naive thing, where you put a D-wave pairing amplitude on this. Well, then you're going to get 8 nodal points. And now you could wave your hands and say, well, the backside is too weak. But that's not going to buy you anything here because you can go to very low temperatures now. You go to very low temperatures and measure the thermal conductivity or the specific heat. And that's been done very carefully, especially by Cyril Proust and Louis Taillefer and others. And they're adamant there's only 4 nodes. There's not 8. Because you can really compute these quantities quite accurately. So this can't be right, and indeed it's not right. So if this was the case, this would be the answer to, this is another possibility. This could happen. You get a D-wave superconductor with 8 nodes, and this is what we'd call DSC star. It's something which is fractionalized. But that's not what we're doing. We are condensing. We're not having a usual BCS transition where we just pair up the holes. You know, this picture is just pair up the holes. If you just pair up the holes, this is what you get. You get a superconductor with 8 nodes. What we are doing is we have a non-BCS transition where we're condensing this Higgs boson. And what that Higgs boson does is it mixes the Bogoliubov quasiparticles with the spin-ons. And there are 4 spin-ons around in the pi flux phase. And so now when you do the calculation, lo and behold, the backside Bogoliubov quasiparticle annihilates with the spin-on, and you get 4 nodes. And that's literally what comes out. Okay, so you get a conventional BCS superconductor, and you really need the spin-ons to make that happen. And you can even get the anisotropic velocities, no problem at all. Really everything which none of the previous scenarios could really make that work. Okay. Yes.
Before you make a superconductor, in the normal state, are your quasiparticles like happy? I don't know, free-ish quasiparticle? Are there anything special about?
So you mean? So here, you know, so out here, there's a lot of gauge fluctuation. But once I go into the superconducting state, I've Higgsed all the gauge fields completely.
Okay.
So basically, at this point, it's just a 6x6 matrix of fermions, spin-ons, and the 2 layers and everything. Just have to diagonalize it. That's all. Of course, you know, we'd love to see a more careful calculation with all the gauge fluctuations, and I've been talking to some lattice gauge theories to do that. At least at half filling it could be done. Yeah.
Before mixing, you have all this gauge fluctuations, so your fermions probably are not.
No, so the only gauge fluctuations I have are on the bottom layer. So what's happened is the pseudogap, you know, the pseudogap has made life easier to me because it has gauged out the top 2 layers completely. So Higgsed out the top 2 layers. So the pseudogap, the only gauge field is the gauge field of the spin liquid. And it is that gauge field that the infinity number of DQCFP talks are trying to understand its consequences. And I'm just treating it as free fermion, and then I'm going to Higgs that gauge field by this boson B. So at this point, nothing is left except the spin-ons and the electrons. And very nicely, I get 4 nodes. Now, of course, there could be a narrow window right near TC where there's 12 nodes, but I think the gauge, I'll have to appeal to the gauge fields to get rid of that. I don't think they'll be there. But at 0 temperature, definitely 4 nodes. Yeah.
So this hybridization between second layer and first 2 layers and superconductivity, is it the same order parameter, or there 2 separate order parameters for those?
Yeah. So this B is a matrix. I mean, sorry, there's a B complex spinner on each side. Out of this B, I can construct all these order parameters. So B is like the square root. It's at one fell swoop. It's the square root of the stripe order parameter. It's the square root of the D-wave order parameter. It's the square root of the current order parameter. It has all of those in it. Depending on how the B varies in space and in its internal space, you can get all of these states. And that's how I get this phase diagram. And depending on the coupling constant of the B Hamiltonian, B free energy, you get different phases. So in the simplest case where B is condensing at zero momentum, then there's actually two components. So B has two minima because it moves in pi flux. So there's a B plus and a B minus. And there's a combination of them, which is exactly the D wave order parameter. So it's a bilinear. Everything is a bilinear, gauge invariant bilinear. These are all gauge invariant objects here. Yeah, this is basically the pairing order parameter. Yeah.
Can you say a bit more about how people conclude there are only 4 frequencies calculated from the experimental data?
How there are only 4? So you measure the specific heat and the thermal conductivity, and those are given by just the ratio of VF and V delta and the number of nodes. That's all you need to know. The two velocities, VF and V delta, which are these velocities. So once you know these two velocities, then you can compute the specific heat, for example. And
How do I know the velocity?
from photo emission, you know the velocities. Those are known very accurately. Yeah, so there's several papers, there are references in our papers that have done this. I've heard this from Louis many times. Yeah.
Are there any signatures of the spin-ons?
Yeah, well, okay.
From the fact that they make.
All right, so so what I'm showing you is what are the uses of the spin-ons. I'm going to show you one more use. But of course, yeah, this is my dream that somebody directly see the spin-ons. At this point, there is certainly a lot of continuum scattering at high energies in the cuprates. So we need a good theoretical model of that with spin-ons and see if we can model the high energy neutron scattering continuum. Yeah, that's one idea. We have other ideas. Yeah, we'd definitely like to have more direct evidence. This is, I make this, I say that this effect here is observation of spin-ons in the same way as Sherlock Holmes' story of the dog in the curious incident of the dog that did not bark. So, yeah, you didn't see the back nodes. So that's proof of existence of spin-ons. Well, okay. Most people won't buy that, but anyway. Yeah.
Can you also explain the intensity on the arcs? Because in the experiment.
Yeah, this is an actual calculation, but this is an actual calculation from the Ancilla model. This is the intensity.
But experimentally, there's more intensity in the middle of the arc. You have more intensity at the.
Oh no, I don't. So this kind of thing we did do. I mean, that's what this calculation is all about. We also look at line shapes and everything. This is in the nodal region. That's the antinodal region where there's a gap.
It looks like on the arcs you have the most intensity in the middle, right?
No, these are the gapped excitations. Yeah, this is
if
the.
If you go to where you show the arcs, they're those. I mean, the red isn't the highest intensity.
Yes, I think you're right.
So you have it the other way. You have more intensity at the.
No, okay. There's other data I should show you. Okay, we haven't looked at that issue, but I don't think that's a real thing. That may be due to superconductivity. I don't know. There's Peter Johnson's data, who's looked at this very carefully, and looks pretty similar to his. I mean, there was also the YRZ model, which fit the data equally well, at least photo emission is concerned. But then it would have they don't have any spin-ons, and now I'm showing you why you need the spin-ons once you go into superconducting state. Okay, so finally, part 5. What about, this I've talked about already. So there's another, so here's something we're kind of predicting, something very interesting that happens on the electron dope side. So on the electron dope side, if you had a regime where there was no long-range order, and there's a tiny window where that may well be the case, you have the electron pockets, which are here. And now imagine this thing with electron pockets, FL star, that goes superconducting. Well, in this case, in fact, the naive view would be here's a D-wave superconductor. This is the Fermi surface, and the nodal direction of the superconductor is here. So you should get a D-wave superconductor with 0 nodes. No, because now the spin-ons actually become the Bogly-Bov-Pasikov. So in this case, we would predict that even on the electron dope side, where the FL star where you don't have any long-range order, you will get a nodal superconductor, conventional nodal superconductor. And in this case, it is the spin-ons that become the Bogoliubov quasiparticles. So it's much more direct. So there is one experiment by Z.X. Chen where he's measured the gap as a function of angle, and it has a maximum away from the antinodal point, and that's exactly what you find in our calculation. This is the nodal point here. The intensity runs out. Anyway, hopefully they'll be looking at this more carefully. So we predict that there will be nodal points even on the electron dope side, even when the Fermi surface has a gap. So you go from a normal state where there's no gap, there's a complete gap in the nodes in the normal state. He says he has a gossamer Fermi surface. Okay, that's good enough, maybe. So there's essentially no Fermi surface here, but there is a Fermi node when you go into the D-wave state. So that's a rather more exotic effect, and let's see. Okay.
Has that been seen?
No, I wouldn't say that. It looks promising, though. First, I have to get ZX to sign on to this and agree to look for this. I don't know. He has his own theory. But anyway, we have an example of a really interesting phenomenon where you can go from a Fermi surface, from metal, which is fully gapped in the normal state here, and it becomes gapless in the superconducting state.
So that's a falsifiable prediction.
Yes, yes. We would love to see something like that happen. The difficulty here is that you have to find, you have to find a superconductor that doesn't have long-range order. The electron-doped superconductors have long-range order, most of them. What did you say? Sorry, I interrupted you.
Falsifiable means it can also be false, right? I know you want to see it.
Okay, well, so I would turn around, okay.
It would be amazing if something very nice.
Okay, so
You're asking if you'll accept the results of elections?
I will only accept it if you can explain all the other things, all the other problems I'm solving. We've got the antinodal photoemission, we've got the 4 nodal points, and now the quantum oscillations. Okay, so this is the recent work by BCS on quantum oscillation in CDW state.
Are you the S of BCS?
Yeah, Bonetti, Christos, and me. Okay, I'll show the reference in a minute. So quantum oscillation. So this is, of course, the quite remarkable discovery of Louis Taillefer from 2007, I believe, where as a function of very high magnetic field in YBCO initially and now in other materials too, you see in the endodope regime these oscillations of whatever quantity you measure. There have been many measurements since then. Of a certain period. If you go to the overdope side, it's a much smaller period. And this, of course, indicates a large Fermi surface. And this indicates some kind of small Fermi surface. Now, before you jump the gun and say this is the whole pocket, no, it isn't. First of all, the Hall effect shows it's an electron pocket. And furthermore, there's a lot of evidence that this only appears in a region where there's charge density wave order. So there's some kind of stripe state which shows you these oscillations. And there have been a large number of papers trying to reproduce this by many people. And really all of them have some problems. But there was a basic scenario that was suggested by Suchitra Sebastian and Neil Harrison, which is the following. So they said, okay, here's your whole pockets. What they said in their paper, well, we have these Fermi arcs. So they didn't even draw the backside. They just said you have these arcs. At least they did some calculations, but anyway. You have these arcs, and now you have a charge density wave. So imagine why the charge density wave moves this arc from that point to this point. So you get, let me do it over here. You get one arc over here, another arc there, another arc there, another arc there. So that little diamond shape is an electron pocket, and that's what's causing the quantum oscillations. So that is Harrison-Sebastian proposal, and it makes a lot of sense. It takes what's seen, the arcs, and the charge density wave, and just very simply builds a single electron pocket. And there's been also a lot of evidence by Suchitra and also Martin Grevin that there are no other pockets floating around. It's just one electron pocket, or no of any substantial size. All right, so that's all great, and we can declare victory with just one small problem. I don't know of any theory that has only one arc. No matter how weak the intensity on the back, it must show up in quantum oscillations. So there was, in fact, a calculation which included the backside by Long Zhang and Jiawei Mei. And we redid it in our formulation, but they did it using YRZ or something. And so what do you get? So when you just add a charge density wave on the YRZ state or the FL star state, you get this alpha pocket, which is the Harrison-Sebastian alpha pocket. But from the backside, you get this beta pocket, this big beta pocket in blue. And here's the quantum oscillations. You see it doesn't look anything like the experiments. And if you take the Fourier transform, you get a large peak corresponding to the alpha pocket, but you also get a very significant peak for the beta pocket. And that's been an open problem for 15 years, or 20 years now almost. How do you explain these quantum oscillations with just one alpha pocket? Okay. And there's also some issues with the specific heat that I haven't put on this slide. But read this paper by BCS if you want to know more. Okay. So what's the answer? Of course, it's the spin-ons. So there's also these spin-ons sitting around. So in this case, we just start from a fractionalized phase. You turn on a charge density wave. You haven't done anything to the spin-ons. They're unobservable. So you don't get a CDW state. You get a CDW star state. So what if you condense this B boson now in a different orientation at this wave vector? So that's what we did in this paper. And what happens is that now these spin-ons mix with the beta pocket. And the spin-ons actually have been moved by half the charge density wave vector because the charge density wave is the square of the spin-ons. And that's exactly what you need for this to work. So what happens is that the spin-ons convert the beta pocket, which is here, to these two delta pockets, here. Now these are much smaller, so they will give significant specific heat, which is actually important for understanding the specific heat experiments of Taillefer and others. But now this delta pocket is so small that it only shows up very weakly here. And these low frequencies, you don't have the field range to see these very low frequencies, and they're probably also very sensitive to disorder. This is a calculation with no disorder. So basically, you just get the alpha pocket. That's it. So the spin-ons, you just put them into this calculation of Long and of Zhang and Mei, and lo and behold, you get rid of the beta peak. You get exactly what's seen. All right, so that's another problem I would like to see solved. So is this observation of spin-ons? No, but it's, I think, quite neat how so many things fall into place once you treat the spin-on seriously.
What makes the amplitude of the delta peak small? Low frequency, but why?
It's at very, very low frequencies. Yeah, I don't know. Maybe the effective mass may be larger here, I suspect. Yeah.
But zero temperature wouldn't matter. Or is it final temperature?
This is a zero. This is a numerical calculation. Yeah.
And this is just one family, or you sum over?
No. This is not a semi-classical. This is a numerical. It's a Green's function calculation using a transfer matrix method. It gives whatever. It's just the Fourier transform of this. The calculation gives you this trace. You compute the Green's function using a transfer matrix method. Yes. Anyway, okay. If you have other ideas, but I think this is a problem that's been nagging me for 15 years. And then I told Pietro and Maine, just put in the spin-ons, and it just worked. Okay. Well, no, they had to fiddle around a bit, and they had some very clever ideas. But yeah. Okay, that's it. So basically, I've shown you, if you, as a starting point of your theory for the pseudogap is this FL star state with hole pockets and a background TQCP nail VBS spin liquid. Then when you confine it, you get just the right type of P-wave superconductor. You get, and maybe even you can explain the quantum oscillations finally. And so now, another interesting point I would like to make is that, there's the backside problem in photo emission, but we've just seen the spin-ons, at least at low temperatures, really don't like the backside. They just get rid of it, both in the CDW state and superconducting state. So maybe if you put in the spin-ons in the finite temperature state with the gauge fluctuation, you would also lose the backside at photo emission. Okay, that's another interesting calculation. If somebody wants to do it, please go ahead. We'll see. But of course, as Lucille said, the best thing would be to actually see the spin-ons the way they're now being identified, for example, in the triangle lattice antiferromagnet and also in the pyrochlore. I think the scope for that type of experiments here. The difficulty here, this is a doped system, and the dopants definitely do change the spin spectrum at low energies, where you get all these hourglass spectrum and so on. And they probably modify things at high energy a bit too, and we need good theoretical methods for calculating them. And so that's the challenge. Thanks.
How much does the result depend on? So the parameters for the spin liquid layer. Is it just the spin-ons with nearest neighbor copying and pi flux, or
that's all? See, so far everything I showed you has been done with that model. That's it. Nearest neighbor pi flux. That's all we did. Yeah.
Yeah. So in this Ancilla model, perhaps I missed your explanation, but you started from decoupled model and with the color gap transformation to get this JK.
Yeah, that's.
Magnitude of JK is uniquely determined by this.
Yeah. So it's JK squared over J perp. It's actually U is JK squared over 2 J perp. Right? I mean, it's worked out in our paper. Yeah.
For this quantum oscillation scenario, would you expect, since this is a very large field, any breakdown orbits to start showing evidence of these small pockets?
Yes, in fact, great question. You do see one such peak in our calculation.
I see.
So there is this F alpha minus F gamma, this F gamma. Gamma is the whole original hole pocket. So this F gamma right here. So that's coming from breakdown. That's the black. The actual pockets are the red and the blue. You see some signal of the black. That's coming from breakdown.
But they're still at small enough.
Yeah, I mean, this is coming. So this is a numerical calculation of this band structure. I mean, in the end, it's a, I don't know, period 4. So it's a 16 by 16 lattice, and then you have to do something.